Alright, this is going to be a video explaining my code that I created for my thesis. My name is Ryan Moeller, and my thesis was about an agricultural robot. And I expect you already know everything you need to know about the background of the project and what this code is designed to do. You can go read my thesis. Hopefully you have that. This purpose of this video is just to describe how my code works. So I wanted to start with this picture. This is the output of the code. Here we have our potato field. This is the irrigation line. And you have the same number of plants, and they're the same set of plants for all four of these. And these are four different trajectories that the robot could take. You can see this is the total distance of the trajectory. This is how many rows it crosses. It's using northing and easting, which is analogous to latitude and longitude. It's just that northing and easting UTM 12N, it's a lot easier to do math on because it assumes that the area that you're in, 12N, is flat. And so you can use Pythagorean's theorem reasonably within reasonable accuracy. Alright, I'm just going to get into the code. This is going to be, there's a lot of code, and I'm going to go into all the detail. So let's do it. I'm using Matlab online right now, and as you can see, there are a lot of functions. These are all functions that either I wrote or I used from other people. So there's going to be a lot of little rabbit holes we go down, but let's get started. So first, XC and YC is the very center point of your crop. I will put a website link here on the screen when I go back and edit this video for a good website that I like to use for converting from like regular GPS coordinates to these northings and eastings. So, okay, phi is the angle from 0 degrees here to increasing all the way to 360 degrees as you go around counterclockwise. So 45 degrees would look like this, and 90 degrees would look like this. And you can also use a negative number if you want. This is the radius of your circle. Right now I have 400 meters set. 50 is the number of potato plants that you're dealing with. Alright, so here's our first function called circular points. If you have your cursor in this function and hit Control D, it'll take you to that function. So here I'm defining what type of random function generator I'm going to be doing. I'm using one, I'm shuffling, which if I remember right, that means you start at a different number generation every time you turn on Matlab, and then twister is the type of random number generator I'm using. There's with everything I'm talking about, you can find documentation on Matlab for all sorts of stuff. So what this is doing is you're taking the center of your circle and you're creating a circle with you're creating a bunch of points within that circle as defined by your radius. So it's just creating a bunch of random points inside of a circle as defined by your center point and your radius. And I believe I copied that function from somebody online. I didn't come up with that. That's what I did with a lot of this stuff. I used other people's work and added to it. So then now what I did was I went into these two vectors, eastines and northines, which these are now the vectors if we pull up eastine. Again, I'm going to hit Control D. It's going to pull up eastine. So now I have 50 waypoints. And then these are just the latitudes, or the eastines, for those 50 waypoints. I'm just taking the first one and replacing it with the coordinate of my robot starting position. So that's what these are doing. And then here I'm forming XY, which, as you can see, is just a matrix. I'm just combining these two column vectors. Okay, these next two parameters are very important. Number of num iterations is setting how many times the traveling salesman algorithm is going to iterate before it stops. And population size is setting the population size. And you can read about how all that works. I'm not going to explain how the genetic algorithm works right now. Just going to explain what you need to know to code with it. Okay, so this is the first actual section that's actually solving something. This section, I am getting into the nitty-gritty. So first, I'm calling this function that I created myself called Reroute DMAT. Okay, so let's start by going to this function actually. This TSP_GA function is not mine. It's a traveling salesman problem created by someone online, Joseph Kirk to be exact. You can find this online. You should look through it and understand it. I'm not going to explain every line, but a couple things, or one thing that you do need to know is, as you scroll down, okay, here we go. I think I missed it. Okay, it's up here. So DMAT is what the author of this code called a matrix to describe the distance between every single point considered in the traveling salesman problem. So if there are 10 potato plants, DMAT will be 10 rows by 10 columns. Column 3, row 7, so the element at column 3, row 7, will be the distance, the straight line distance between plant 3 and plant 7. Okay, so that's what DMAT is. And in this code, if you do not supply DMAT to this function when you call it, it will create its own DMAT automatically. It's going to do that all with this one line of code. And it takes a lot of time to understand this one line of code. What I had to do was break it down and just mess around with this one line of code. And I'm not going to go into all the detail of it because it takes a while to learn. But it's going to create the DMAT. Okay, so as I describe in my thesis, the problem is that the straight line distance, for example, between this potato plant and this potato plant is blocked by this irrigation line. So the actual shortest distance between this potato plant and this potato plant would be a line that goes here and here. So that DMAT matrix needs to reflect this distance that I'm motioning right now with my mouse. Okay, so that's what this function does. It's called reroute DMAT, and all you have to do is pass it your x, y, which is your eastines and northines for all of your potato plants. You need to pass it your center coordinates of your field, the angle at which the irrigation line is at, and the number of points. in XY. And you're probably going to notice I'm not a computer programmer, so there's probably some things I do here that are that don't make 100% sense, that it could have been done more efficiently or effectively, but it works. So let's go to this. I'm going to hit Control D now to open Reroute DMAT. Just to keep things neat, I'm going to close the TSP_GA function. This entire function is based off of that one line of code in the TSP_GA function to create DMAT. It's based on it, so I can't take credit for how complicated some of this is, because I was using the ideas in that one line of code that I was just telling you. But basically what you do is first you have to start by taking all of your waypoints in XY and transforming them so that the center point is 0, 0. And this is, if you read my thesis, this is necessary because of the way and what I'm kind of about to explain. It's necessary because of the way the mathematical tests I use work. And then you also have to rotate it by -v, so that if your irrigation line is in the 45-degree angle, you're rotating it by all your points by -45, so that from the perspective of the points, it looks as if the irrigation line is actually in the 0-degree position. Again, this is important because of the way the test works. So first step is find the angle between all pairs of points in quadrants 1 and 3. So this is quadrant 1, quadrant 3, and I'm finding the angle between this point and this point and this point and this point. So the angle between all the pairs of possible points in quadrants 1 and 3. And that gives me this, I guess this would be a matrix. That gives me this matrix right here. That's the angles. Now I find the angle between all the points in quadrants 1 and 3, but not between them each other, but between the center coordinate 0, 0. And what I'm doing is I'm taking a mathematical test to find which of these angles have, if the angle I'm trying to remember which way it is, if the angle between the coordinate and 0, 0 is greater than the angle between the coordinate and its other coordinate, then it needs to be rerouted. And I explain that more thoroughly in my thesis. Let me actually pull that up here just a second. Okay, so this is on page 26 of my thesis, where I explain this mathematical test. So if alpha, the angle between your waypoint and your center, is less than the angle between your waypoint number 1 and your waypoint number 2, what that means, if that's true, if alpha is less than theta, then the points have a direct path between them. But if, in this case though, that you see in the picture, if alpha is greater than theta, they need to be rerouted from here to here to here. So that's what this section is doing. I'm finding those reroutes. Now I'm going to repeat the whole process, but for quadrants 2 and 4, it's very similar. You just have to switch a couple things around. That's same here. Now quadrants 1 and 4, as you can see, all of them need to be rerouted. Okay, so this line of code is, oops, So this section of code is just finding all those pairs of points that include a point from Q1 and Q4. So now I'm combining into one giant matrix all of the paths that need to be rerouted. Okay, so here I'm taking DMAT and I'm using the same DMAT as is used in that TSP_GA function. I'm taking DOrigin, which is very similar to DMAT, except it's the distance in between the origin, so 0, 0, and each point. And now I'm using that to reroute, right? So I need that matrix because if this needs to be rerouted, then I need to replace the value in DMAT with the value of this distance plus this distance. Okay, so that's what this is doing. And then this one, you need to make sure your diagonal is full of zeros, I believe. And then this is your final matrix. So this distance cost matrix is a n by n matrix. So if you have 50 potato plants, it's 50 by 50. It's 50 by 50, and it's going to have your distance between every single waypoint with every other waypoint. But if that distance crosses the irrigation line, it's changed to the distance from one point to the origin to the other point. Okay, so that's reroute DMAT. That's what that's doing. So now in this next line, is a function called rows DMAT. I'm going to hit Control D to open that one. So now in this rows DMAT function, I'm going to be generating the rows cost, which is again going to be an n by n matrix, but instead of the distance between each point, it's going to be the number of rows required to be crossed to get between each pair of plants. So essentially what this is you are finding the horizontal distance between all the plants, not the hypotenuse, just the x or horizontal axis between every single plant. That's what this node is here, just looking at the x-axis. So but again, you have to take into consideration this a plant here and here would need to cross this many rows and then this many rows again to get to this plant. So that's what this all of this is doing. Just using the same process as what I described before. One thing to note why this function is so much shorter is I'm passing that rerouted matrix, which that's just ones and zeros. There's a 1 every time there's a pair of plants that needs to be rerouted because of the irrigation line. So you have to have already have used reroute DMAT in order to use rows DMAT. So I'm using that here. So that just makes sure they are run in the correct order. Okay, so once you find those two, that's the hardest part about what I did, was finding those two matrices. And so for the genetic algorithm, it needs a cost matrix, which in this, how I've set it up, in this section is I'm taking the distance between each plant and adding how many rows required to be crossed between each plant, and that'll be my total cost. For this section, I'm just doing distance, so this is a 0. So now it's time to use the TSP underscore GA. To do that, you need to set up this user config variable. So I'm passing my XY. It's looking for a matrix called XY, which contains all your latitudes and longitudes, which in my case, I've just called it XY. Now, if you don't give it the cost matrix, it'll formulate its own, like I said before. But here I'm telling it that I'm going to pass you DMAT that I've calculated myself, and I'm going to pass it this total cost matrix. I'm going to define my own number of iterations, which is num iterations. Same with population size. I don't want to see my progress. I don't want to see the result of the convergence, but I do want to see the weight bar. That's what this line of code is doing. And then here I'm going to actually call the algorithm using these parameters. Okay, so after this line of code is run, you'll see a weight bar, and it'll progress, and then when it's done, it's done. So then I'm pulling out a few important things from this result structure. I'm pulling the optimum path, pulling the total distance of that path, and this is a function that I made. Oh, so is distance. So if you go to find distance by hitting Control D, it just is running through the XY and using the optimum path vector, and it's just calculating, just adding the distance up to find the total distance above the optimum path. And it's similar for the number of rows crossed. Excuse me. So that's what those are doing. And then I go on to do, so this was distance cost only solving. This is plotting it. So then I'm going to solve and plot just the rows cost. Now, the only thing changing in all these sections is just this line right here. I'm changing what the total cost is. And then running the algorithm based off of that new cost matrix. So I guess technically, yeah, I didn't need to refind the rows cost and the distance cost each time. But I mean, these lines of code take like less than a second to run, so it's not a big deal. And then let's just run this code and see what it does. I have iterations and everything pretty low so that it runs faster. It can take several minutes if you have a lot of plants and a lot of iterations and all that. Okay, awesome. So here's the first time through considering just the straight line distance between all of the plants. And you can see it's the smallest distance of all of them, which makes sense because we were only wanting the algorithm to look at distance. And it also has the highest number of rows crossed. So here, if you look at just the number of rows crossed, it's the minimum number of rows of all these 4 options, but it's also the longest path. And the graph, this makes perfect sense. And lots of vertical, because this is assuming the rows are going up and down, north and south. So there's lots of, this path means that the robot, if it started here, would cross over to this row and then go straight up. And then from here to here, what this means is the robot would have gone straight over a few rows and then all the way down. So that's what that's signifying. Now, when you add both of them together, you get a distance which is a little larger than the first solution, but you do have a lot fewer rows crossed. And if you play with, if you like weight the rows more, then you'll get different results. So that's that. Sometimes with a low number of potato plants, you get weird results. So 50 I just used to solve everything quicker. So one thing I skipped over how I'm plotting everything. Let's see so this draw outline function, I'm hitting Control D to open it. All it's doing is it's plotting our center point, it's drawing the outline of the circle, and it's plotting the irrigation line and labels. That's all draw outline is doing. This is actually plotting the points, the potato plants. This is plotting the starting location of the robot, so this blue star. And this is plotting the optimal path with a blue line. Now this these label and text functions are taking care of this distance and this rows number right there. It's putting that on the graph. So that's what's going on next. I believe that's it. Yeah. So at the very end of this code here, I have a couple other functions. Okay, so I've run the code. I've uncommented and run the code here. So this is solving the same thing we did before, but using the multiple integer linear programming algorithm instead of the traveling salesman, instead of the genetic algorithm. So this is another algorithm I pulled from online. I didn't create it, but just some of the syntax is a little different. So same concept, you're going to generate a cost function, but the formatting and just what each thing is called is a little different. So I've split my northings and eastings in these two lines into two different column vectors. And I use reroute dmat just like I did before, but I have this function called int. And what this is doing, Control D to look at this, it's the same thing as before, except this algorithm doesn't want an n by n matrix. It wants a column vector of all of these distances. So that's what this is doing. So we find the distance matrix, and then I'm calling this algorithm. So Control D to open it up, and you can look through this yourself, but just kind of a brief overview. I'm giving it the distance matrix I want it to use. If not, it's going to calculate the distance between each point by itself, not considering the irrigation line. So we want to use this distance. It's very different than the genetic algorithm. You have these equality constraints. I didn't do anything with there. I didn't change the binary bounds. None of this I actually changed. Just needed to get the right type of distance matrix. So you run it, and it gives you a solution. One thing about this is the solution is generally going to be shorter. It's going to be better than the genetic algorithm with regards to how short the overall route is. But sometimes it can take longer, sometimes it takes shorter. It's pretty inconsistent. And so here, this code it's converting from UTM to LLH, which LLH is latitude, longitude, and height. So it'll give you back your vectors in something that makes more sense that you could plug into Google Earth. And then you can also use these codes to save, a vector of the optimum route to a KML file, which Google Earth likes KML files, or CSV, same thing, Google Earth likes CSVs. And then this line here, this print, just saves a .png file of your graph. So this is my code. By far the most complicated thing is this reroute dmat. I just hit Control D there. This reroute dmat function took a lot of thinking, and I know I just kind of brushed over a lot of the lines because honestly it's been a few months since I wrote it, so I'd have to go back in and dig deep into it to understand every little thing. But basically, if you want to understand this better, what I would do is I would take, so here in this function, everything's being passed into it right here. But what I would do is I would come here and I would copy and paste the code directly into here and save as its own .m file, not as a function. So I would delete this line so that you're generating everything you need in the code itself instead of getting it from other functions. And then you can run this code just by itself and you can track variables, see what they're doing. Essentially, like I said, you're using a matrix of ones and zeros to find which ones are rerouted, and then you're timesing, at the very end. Oops, wrong scroll. Then at the very end, you're timesing the distance matrix with that ones and zeros matrix, so that you're left with the right distances for those that need to be rerouted and those that don't need to be rerouted. I hope that helps with the code. Okay, so I forgot, I need to show you one more thing that I did. I'm going to just run this code and show you what it is. So let's hit run. I didn't use very many points, so it will not take very long. Okay, so this first figure is just showing you your waypoints. These red areas, this is your distance matrix, the n by n distance matrix. So it just means that like waypoint number 20 and waypoint number like 43, it's a yellow color. So the distance between those waypoints is greater than, say, these blue ones over here. This is showing the optimum path, and this is showing this axis is the total distance of the optimum path with each passing iteration. This figure comes up when you are calling TSP underscore GA, and you have the show result as true. So if you want to see like the convergence or whatever, you can have that set to true. So what this code is, this script is doing is it's just like the previous one. You are generating points, then you're going to solve it and pull out your optimum distance, the minimum distance. And that is plotted here. Okay, here's my irrigation line. Now, what happens is, and what I explained in my thesis is, if this irrigation line is moving, say, counterclockwise, then when this robot starts, let's say it starts in this direction. Okay, it's moving along. If it took a long time to get all the way to this point right here, this plant right here, this irrigation line might have moved move to this position right here. And then this whole path would no longer be valid. So the way that I proposed in my thesis to handle this is you calculate this solution just like we've done here, and then you find and then you know how fast the robot is. Sorry, just a second. You know how fast the robot is and how long it'll take to run this path. Okay, you also know how fast this irrigation line is. I just used some values online, but in real life a farmer would know the exact values. So you will know how far this irrigation line goes. So what I propose is, after you find this optimum solution, is you find the wedge or the pie slice that this carves out, and you remove all waypoints inside of that wedge, and you resolve the TSP problem, but not including those waypoints. So that's what this has done. Now the other problem is, not only will the irrigation line move this way, but it just watered everything behind it. And it waters so heavily that even large tractors can't pass through how thick the mud is. So there's a certain area, which would have to be decided by the farmer or by trial and error. There's a certain area behind the irrigation line that also is impassable because it's so muddy. So that's what this area is back here. And so first you would find the shortest route between all remaining, waypoints that aren't inside of this pie slice. And then, so the robot goes, does its thing, comes back. And then after a predetermined amount of time through trial and error, you'll know how long it takes for this to dry. Then the robot will go back and using TSP, find the shortest route between all the remaining potato plants. So that's what this code is doing. Okay, so it solved it. It's plotting the optimum route, and it's done. So that's figure 2. Now identify points inside of the segment, remove, resolve the problem, and replot the problem. So this is just taking my mud angle, which is this guy right here. I'm saying that my mud angle is 45 degrees less than the irrigation line angle. Now you segment test is going to find all of your points on the inside, all of your points on your outside. Okay. And delta is the new angle, is this angle right here. Okay. So then you're going to resolve the TSP problem, but this time instead of just using XY, you're using XY outside of the segment. So just these right here. And then you plot those points, and then you're going to go back, and this time instead of using phi, you're going to use delta, the new location of the irrigation line, and you're going to solve the TSP again. But this time, instead of XY and instead of XY outside, you're doing XY inside. So that's pretty self-explanatory. There was a little bit of tricky math coming up here to the segment test. So I'm going to hit Control D to open up this function. So you need to know the speed of your robot, which I'm finding here. This is the RPM of the motor, or of the motor after the gear reduction. This is the diameter, so you can calculate your robot speed, and this is taking the overall distance, this entire distance, dividing it by the robot speed, and that's how many minutes this path would take to follow. And this is assuming that the robot has enough battery power to do this in one trip. Future work we'll have to incorporate a way for the robot to know when it's going to recharge, or if it's going to need to recharge, and how it's going to handle all that. Okay, so P speed is the speed of the the irrigation line, and this code is just this code is just finding delta, the new location of the irrigation line after the robot would if it did go to every point, how the new location if it went to every single plant, which you can't do, but we're just using that amount of time as a rough estimate. And here we're rotating all the points by the mud angle. This time I converted from Cartesian coordinates to polar coordinates, and you'll see why in a second. So beta is my xy in polar, and I'm converting from radians to degrees, and I'm making all of my angles be from 0 to 360. So now with that, we can test if we know that this is a certain angle, anything less than this angle or greater than the mud angle, less than the mud angle or greater than will be inside the segment, and everything else is outside the segment. So that's what this code is doing. That's the segment test. And trying to think if there's anything else here. So this was a little tricky. It was just easier to use polar coordinates because dealing with angles and segments, polar coordinates lended itself to that better. Okay, I forgot another thing to explain. So when you are, this is going back to just the simplest problem. You're just finding the optimum route and plotting it. You find, so here we find GA distance. And here is our optimum route. So this is just a vector. So this is just saying, okay, let's visit waypoint 14, now 24, now 43, now 35. So if you plot this vector, it's just going to have straight lines between all these points. But we don't actually want a straight line if like in this example, if this was rerouted. Okay, so how do you plot the optimum route reflecting those routes that were rerouted? The way I got around that is here's my plot route function, which I call, let's see. Let's find it. Oh, here it is. Oh, wait, no, that's not it. Here, yeah, plot route. So after I draw the outline and plot my waypoints and X's, I need to plot the actual route. So we come here to plot route, and it's just pretty simple. I'm stepping through the optimum route with X1, Y1, and plotting them as lines. Now, this is another function called the intersect test. And this was a way of finding if two lines intersect that I found online. I did not come up with this method of finding whether or not lines intersected. But what this is doing is if these lines intersect with, what this is saying right here, if they intersect with the irrigation line, then what I'm going to do is instead of plotting from the first waypoint to the second waypoint, I'm going to plot from the first waypoint to the center of this crop to the next waypoint. Now I say first waypoint and second waypoint because plot route, because this is a for loop and it's stepping through the optimum route. So first and second waypoint, second and third waypoint, third and fourth waypoint, it's comparing all those pairs. So that's what this intersect test is doing, in case you were wondering.